Thank you for the introduction. Yeah, so this is totally like an integral part. It's cool. Yeah, so the work was joined with Julian Klaas. And so now let me try and explain calculus. So so I fix f over b. So that is a finite expression. And gamma f is going to be an absolute Galois group. Okay, now I want to fix also some coefficients. So L over 3. So this is my coefficient thing. So this is a finite field extension, ring of integers O, uniformizer, and K is very. Now, so there'll be a Galois representation, but now I want to explain this generalized reductive group bit. So what I'd like to fix, G, so this is a smooth undefined scheme over O, such that its neutral component, reductive, and the component group G modulo G0 is like. So
family tau?
Huh?
Do you need family tau?
Thank you for this question. This is what I like. This implies that this is automatically a tau, and if you don't like this kind of thing, you can think G equal to G of n. This is an example. Right? G of n. And so I should mention that in special case, I studied together with Berkeley and Usher and Lee. Right down. Okay. Now, so this is like quite a general setup, and so in the proof there was there's like induction of over the dimension of G, and the G's that come up in this induction I cannot really control them, so that's why I have to work out of these things out of necessity, my argument, but I should. I should allude to the main example that I want to that the setup handles. I mean, if I have H, a reductive group over F, then G can equal the L group of A. So split over E over F. So this is finite Galois. So then there's this. Then you can associate the H and L group in the Langlands program, and typically this will be a constructed over complex numbers, Q of R. But the construction, this is somehow out of the root data, and this root data, I mean, you can do this once you have this root data information, you can do this over any scheme basically. So you can do this also over O. And the component group will be Galois UOF. So this will be a constant group scheme, and this will be my G model. Okay, so now I want to introduce a representation that I'm wanting to form. So I give myself a rho bar, a Galois representation, the GK. So K is this finite residue field and continuous. And I would like to look at its deformations to understand its deformation space. And this came up in Toby's talk yesterday. The difference is my setup is purely local, so it's easier. And there are no deformation conditions. In the sense that Toby was interested in crystalline lifts of given weight, I want to look at all the lifts, basically, parameterize all the lifts. So the way one formally sets this up. So this is Mesa. Right. So I want to study deformation theory of one. So the way this is done, one looks at a function. This is category A for Athenian. Oh, so this is the sets. So this is Athenian. So this is local Athenian O algebras. A and A, and with a residue field A. And now, so this functor is defined as sending such a ring to O gamma F G of A. This is continuous, such that rho of G is congruent to rho of R of G for all D in so if your G was GLN, this would be just a congruence condition on a matrix entry, right? Okay. And so Toby well put complete local Noetherian rings here. I prefer to work with Athenian rings. But it's better. Fine. So now, so this thing, this functor is rho represented by a complete Euro O algebra. So this will be denoted box rho bar with residue field. Okay. So this box is framed. So this refers to the fact that I'm not modding out any automorphisms here. Okay, and right. So so what we do and what I want to explain in this talk, so we study so let me
So can I ask a question about the definition?
yeah.
So in this example where it's an L group, I would expect not to get a homomorphism, but like you would restrict to just like L homomorphisms, like things that so that the projection of the Galois group is actually like constant.
Sorry, but these are still representations, right?
Yes.
But once you deform this, you cannot really vary the component group. I mean, there is no, look at the tangent space, it's fixed. And in fact, this is what I'm gonna do in just a moment. I'm gonna, so you can shrink this group G, you can cut down this group of components by replacing group of components by the image of rho bar. Okay.
Yeah, so I think you're saying in particular that if it's an all homomorphism at the rho bar level, it stays.
Right, exactly, yes. Sorry, yeah.
Thanks.
Yeah, so imagine if my G0 was trivial, so this would be just a component group, and when you look at the tangent space of this functor, there's nothing there. There's no deformation. All right, so let me. Theorem. Okay, so as I already mentioned that in the case that Iyengar, so I should say this is actually Iyengar. There are like lots more Iyengars and Paskunas in this world. So we did this for G equal to GLD, right? And so that's already a good start. But now I have to tell you how to go. So like this ring is O flat, complete intersection. Right. Relative. Take dimension of GK. So we take the spectral fiber, that's dimension, and then multiply this like that. 3 plus 1. Okay, so in Toby's talk that became terminology expected dimension, and with some luck, I'll explain in the course of the talk why this is the expected dimension. So one of the reasons one might be interested in this, so this property was complete intersection, or expected dimension. This kind of implies that if I looked at some derived version of this problem, in the sense of Vytautas Paskunas, that this would be the same. This would be the same as the usual deformation theories. Don't gain anything. And then, so for GLD, this was used, GLN, this was used by Yumin, who derived some sort of version of, defined a version of derived Hamilton G stack, and then coincided that, well, showed that it's basically the same as the usual Hamilton G stack. So, right, Hamilton G stack. Yes, this is the reason why I breathe. Let's see. So these rings, they kind of stand up as vessel rings for this Hamilton G stack. This Hamilton G stack is somehow modular space of the phi gamma modules or whatever. For a fixed G, and these rings they kind of encode local information about it. So if once you prove something about this, you prove something about Hamilton G stack, and yeah, this might be useful in periodic Langlands, who knows? Right, so that's why. So yeah, so suppose this was motivation. So this is motivated. But there are like more down to earth motivations. So one immediate corollary, you get that there exists rho here, G and bar, lifting. Yeah, so this ZP bar, which is a ring of this bar. And this follows immediately from this O flatness. So this is O flat. So if you invert P, you get something which is non-zero. And for such rings, you know that residues of the maximal ideals are finite extensions of QP. So okay, so then you embedding this into QP bar, and you get a Galois representation. So of course, yeah, this is not an obvious. This is not obvious. But of course, I mean, Hamilton G is for GLN. They can prove much better results. Additionally, say for GLM imposing Bialy-Hodge type of conditions. So we don't get it, but we can do very challenging.
You get the reducible bits.
Yes. Yeah. So. Rho is absolutely reducible in the sense that its image is not contained in any parabolic subgroup. So in fact, we show that absolutely reducible locus is dense. Okay, so let me move on. Okay, so now there's also theorem 2. So we show that this is 1 over p. This is normal, and as a consequence, it's reduced. Okay, so this is already completed. Yeah, so will not be surprised to you, and this is says criterion for normality. So normality, I mean, already know when it's completed the section, and then you kind of have to show regularity for dimension 1. This is kind of what happens in the proof. And once you know that this is normal, this contains it as a subring, and normal implies reduced. So this thing is also reduced. Yes. Right. Okay. So now let me carry on. Okay. So essentially, like for these statements, we can replace L by a finite extension. And this implies that without loss of generality, I can assume that this connected component is split over O, and the component group is constant. It's constant, and then there's a further trick which I alluded to without loss of generality. This composition gamma f g k g modulo the component group, which is surjective. So this is already to be assumed constant, and I have this map, and then I can take the image, and then so this is some finite subgroup, and then I can pull this component group back. So I replace my G by a smaller subgroup, and one can check that this deformation functor it does not change. So GE be the kernel of this map. So if I do this, I can identify this finite group with this component group with Galois E to the F. So I get myself in a situation which is kind of similar to this picture. It's just I cannot assume that there is a semi-direct product. I mean, it might not be any clear. Okay. And then the proof it kind of proceeds in 2 parts. So as often is the case, so there's like a torus part and there's a semi-simple part. Okay, so let me explain torus case. So I say generalized torus. So here I assume that that this connected component G0 is a torus. Is a torus, and I can write this G0 as spec of M. M is a character like this. So for example, if G0 was Gm, then this M would just be then. And in general, this is a finite free set module. And so now you have an action of this Galois group on this M. So this component group acts on G0 and it acts on a character like this. We'll get an action of so what comes in there is the following gadget. So we take this module M. So this is some free finite free module over Z. The tensor is over Z with the absolute Galois group of E. Take abilization and maximal Pro-P quotient, right? So this is this, and then we take the Galois F. So then maybe just put this in. So this is a finally generated CP module, and kind of using glass field theory, we can show that we can compute the distortion part. So the torsion part looks like this. Then ZP R1. So R1. So this is going to be rank M times plus M, the covariance of this problem. Okay. So I'd like you to believe this. This is some computation involving local classical theory and some arguments in C and proceeding. Yeah. So doing numbering, so theorem 3 says that if D0 is a torus, then
So the torsion part does not depend on M.
the torsion part. Yes. You're right. Sorry, I'm not saying wrong. Thank you. Yeah. So, thank you for this comment. So, by classical theory, this is E times, and I take Pro-P completion, right? Yeah. So this P power roots of unity, they sit inside here, and of course this factor remains. So. So this is a finite CP module, So I can take this completed group algebra. And when there are some extra variables, Z1, ZR2, so this R2 is an equal to rank Z n minus rank Z and so these variables, they kind of related to G0, which is commutative, modulo the center of G. So G is in general, it's not going to be commutative because of this component. And you see there's like some covariance coming in. And this is the dimension of this. Okay. So let me maybe note this. So this is a finite abelian group. So this is isomorphic to O mu. This group algebra. Okay, maybe I should take some on. Where I is now, if you add I is R1 plus R2, and with a bit of luck, I would get rank Zm times F QP plus 1, which is what is claimed in the theorem. So, so in particular, irreducible components find bijection with characters, so it's mu to all times, and are formally smooth. So if I have a character, maybe so I assume that my O is large enough to contain, let's say, all people whose of unity. Then once I have a character, I can specialize this part, the O. So then this is going to be O. And this is something going to be, this part is going to be formed. Right. Okay, so yeah, sorry. Okay, so this is proved by closely reading Langland's paper on tori. So for Langland's correspondence on tori. So the key point to understand the function that we send this AMA Z1 continuous co-cycles with values in GF. And you take home as a Boolean group simply M to 1 plus MA. And this functor is represented by this ring. And somehow Langland's, these type of things come up in Langland's correspondence for tori. So usually in Langland's correspondence, you take it up to G0 conjugacy. So this amounts to replacing the Z1 by H1. Good. So let me just give an example. So hopefully audience will spring back to life. Okay, so what happens if you take G equal to GM? So M is and Z, as I already explained, and E is equal to N. Right, so in this case, this functor just Z gamma F 1 plus MA with trivial action. Right? And this is the same thing as Hom. So this is just continuous gamma f 1 plus MA. Right? But this is a finite P group, a linear P group, so this factors for linearization maximal. So what you get then, the ring that you get is gamma f, the completed group algebra. So I already alluded to you that this is the same thing now if I take f and I take, so for P completion. But now using this arguments of there, you can show that as a ZP module, this is isomorphic to 1. So this is for an ramified direction, and this over PP. So this is using like some exponential now and so on. Good. So yeah. So are there any questions for the torus part? So I'd like to move on to a simple part. Okay. So we can understand this deformation ring well for Corey by just basically solving deformation problems more explicitly. And we went to a study. Where we call this? We went to study the general problem. If you're splitting up into two parts, so you have like a quotient G modulo G prime. So this G prime, this is a derived group of connected components. So now this G modulo G prime. So if I look at G modulo G prime, connected component of this guy, this is the same as G0 modulo G prime, and this is a torus. So this is a torus. So, and this means that, so if I have this representation as before, to GK, I can define psi bar as composition of psi with rho bar. This is going to be GF, G modulo G prime. Okay. And so we understand psi bar. So let me just add the group so that you know which group I'm talking about by the previous section. And once I have the deformation of rho bar to G, I can just mod out this G prime and get a map between deformation problems. So and phi induces a map G. Theorem 4. and says that this math is flat. Fine. And if phi 1g prime is a phi, then induces projection between reducible components. Components. Right. So what is this guy? So
Can you show us that board again?
so so we have this group G prime, and you have this central simply connected cover, and there's phi 1g. This is a kernel of this. This is some finite diagonalized subgroup. So example. So if G is PGLD, so when you have PGLD, this cover will be SLD, and then you have mu D. And this thing is well, say in characteristic P, mu D is étal, if and only if P does not divide P. I mean, characteristic 0, so if I'm overfilled, so mu D would always be this. So if G was something like GLD, then G prime and the simply connected couple would be the same thing. So this would be trivial, so this would be étal. Right. So how do we do this? Okay, so recall that the reducible components of this guy, they're parameterized by characters. I times and to it. Okay, so you can associate irreducible component. And our theorem 5 says that if phi 1 G prime is étal, then this ring and a special fiber are complete intersection, regular for dimension F or QP, and normal. Okay, so to prove this is also CS criterion for normality essentially. But once I know that say this ring is normal, I know it's a product of it's a product of normal domains, but it's a local ring, so it has to be an integral domain. How it works, and with this kind of argument, then you can determine irreducible components. You can prove this theorem for this. Right. So I try to somehow indicate how I get all these nodes, but so far now I'd like to talk about theorem 1. So you can kind of see that this is something that I should not explain. like to. Julian Paskunas. Right. Here one. So this is so this was this expected dimension argument that's going to come now, and this is something that's maybe from the 80s. So so what knows that this ring will have a minimal representation. Fs. So this R is dimension A of flow cycles, continuous flow cycles for gamma F with values at rho bar, and S is dimension H2 gamma F at rho bar. So this ad rho bar.
Sorry, this is the second little r you've defined. So there's another little r on the
Yeah, so these R's, you've got to roll with them, yeah. Okay. So this is going to be a new R somehow. Sorry. So you have like V G of K. You're right. So as a K vector space, it's just a Lie algebra of this group, and there's such adjoint action on it by G, and then you compose this with rho bar, and you get this R rho bar. And if you compute, like, if you evaluate this deformation function to dual numbers, then I get a vector space of dimension R. And then Mesa has an abstraction theory saying that abstraction to lifting lies in this H2. So you get such thing. And one thing you can deduce from this is that the dimension of the rule dimension of what I get about is special fiber. So this is greatly equal to R minus S. So you see, like, if I didn't have this relation, so this ring, okay, so special fiber, so this gets replaced with K, so this has dimension R. And every time you cut out a relation, the dimension is either stays by the same or goes down by 1. That's how you get this bound. So it's R minus S, this is the expected dimension. That sort of came in talk in a more complicated context. Yeah, so it's always the same. Okay, so I'll explain this in a moment. But an argument with Euler-Poincaré characteristic shows that this is what we are after. Okay, so this dimension is the same as dimension of a Lie algebra, the K vector space. Right, so we have like an exact sequence of we have four cycles, and we can map them homology. And okay, the kernels, they're the co-boundaries, but so it's subject to rho bar, and the kernel of this is H0 rho bar. Okay. And then you can calculate the dimension of this in terms of these two guys and these guys. So you see this ends up as a 1 here, and the other, you get like an alternating sum, and there's like Euler-Poincaré characteristic formula, and this thing just comes out. So this is good because so now there's like a little commutative algebra What? So now, if we can show that if we can bound a full dimension of a special fiber by this expected dimension, then the sequence, the uniformizer, and F1 to Fs can be extended to a system of parameters in O x1, xr. Just by basically, you just pick a system of parameters, this thing. But this ring is regular, it's a regular ring. So this means they're part of a regular sequence. Regular sequence. And then what you get, by definition, you can deduce that this is complete intersection. Now there is this second observation. So you see, if we had like H2 ad rho bar is equal to 0, so if the obstruction vanishes to lifting vanishes, then this S is equal to 0, and this ring is formally smooth. And we win. We win because R minus S is the expected dimension, and this is exactly what we want. Okay. Good. So now, but you kind of see that this is not going to happen very often. And the reason is that we know that, well, might not on flatness. So the map is flat. So we know that this is going to be flat over like this fine group algebra of this finite abelian group, and this means that a special fiber will be flat over, this special pi over this, and this is something non-reduced, right? So if you get lots of roots of unity, you know that this cannot happen. But so you remedy this following some ideas of Kissen. So again, this is like Kissen considered presentations of global deformation rings over local deformation rings, and we kind of do this maybe in an easier context. So what you can show is like, well, basically, okay, using this ideas of Mesa, you can show that this ring can be presented. So psi bar GG prime. So this is the ring that this is a torus thing that we can understand. So okay, so maybe I should put a prime on this R. Modulo F1 S prime. So these are going to be different Fs. I'm not going to put a prime on them. So now this R bar, this R prime, this is going to be now dimension K, Z1, gamma F, at 0, 1, and S prime, this is going to be dimension K, H2, gamma F at 0, bar. So now at 0 bar, So this is the Lie algebra of a derived subgroup with adjoint action of G. Right? So the expected dimension of, if you compute R prime minus S prime, you get basically a dimension of G prime. Okay, let's specify one. F P plus 1. And the dimension of this guy, it kind of had like a similar shape, but instead of G prime, you had like G modulo G prime, and you add them, the dimensions add up, and you get a result, right? Get the right bound. And now you have like a more chance of this thing working. So if S prime is equal to 0, then you can reduce, but this is formally smooth over this O mu, this group algebra, and then you put these, so let me call this I again. Yeah? The expected dimension. And yeah. Right. Okay. Okay, so let me so I think we'd like to prove this. But now I know it's enough like to bound the dimension of the ring. So instead of treating these representations individually, what we do instead, we kind of define a moduli space and bound its dimension. Okay. So we construct affine E, and the notation is like X gen. Well, I guess it depends on G and rho bar, semi-simplification of this rho bar. So this is going to be affine. So right, so I guess I'll well, this is clear. Relate this to A generic. A gen stands for generic matrices. So over this guy, you have like universal representation. F, G. Okay, so yeah. So maybe because I don't want to give exact definition of the space, but let's say you were studying, like say Simpson did, representations of like surface groups, right, which are discrete groups. So what you would take there over C. So what you take there, you take representation variety, right? But now there's no topology. And if we did this, we'd get some non-continuous representation. So this is kind of bad. So we kind of have the difficulty is building in continuity in here. And I should say, well, if G is GOD, then it's been studied by Carl Wang Eriksson. Building on results of Chenevier, who was building on results of Procesi. Okay, so we generalized these things coming up in the work of Wang Eriksson. So on this scheme, we have an action of G0 on this reductive part, and an important ingredient is to consider is GID quotient. So in the work of this kind of came up briefly in the work of Petrov. So this would be something like character variety. And one of the features of a construction such that one. So if I look at FP bar points of this X gen G, so they correspond adjectively to continuous representations rho gamma F G FP bar such that the semi-simplification of this rho is the same as semi-simplification of rho bar. So we don't vary like all representations kind of so this is what it is on FP bar points. Now the connection to the problem that we're interested in is true that as such at x x gen if I look at a local ring at x and I can complete this is naturally isomorphic to this rho x. So rho x is the specialization of this universal representation at x. So, okay. So this is an important bridge between going this scheme x in these rings. Now, another important part of the feature is that this nav phi is of finite type. And this GI3 quotient is spec of R. This I is a complete local Noetherian algebra with residue field. Okay. So, I mean, okay, so this kind of comes out of the construction, but with this R, we can use this R to encode the topology. Okay, so in particular, we know that this generic is Noetherian, right? And enough to bound dimension for generic, because if you can bound the dimension of this scheme X generic, then you can bound with the dimension of the local rings, then you can bound the dimension of completions, and then you can bound the dimension. So it works. And now the way we do this so somehow there are two steps. So we look at the locus U. So this is X, and X generic, such that H2 gamma F B G. So now this is the Lie algebra of the simply connected cover. Since X is equal to 0. And show if U is non-empty, then it has the right dimension. Okay, so so feel like if this G prime was already simply connected, then this would be already the D prime. So vanishing of this would imply that this completion but this deformation ring is formally smooth over group algebra of a local ring, right? So if not empty, we can control this dimension, and then two show that this x gen minus u, so its complement has positive dimension. So if you can show this, then you can conclude that it is non-empty. Right? But the way you do this by treating this complement, you kind of relate this to, let's say, x gen h of groups of smaller ranks. So let me just write one position, and when I'm done. So suppose that G is semi-simple over some algebraically closed field, kappa, and H in G is reductive. If I take Lie G prime, so the Lie algebra is simply connected kappa, take the dual.
You don't need the prime. Use already seen it.
Thank you. So I take the dual and I take H invariance. If it is not equal to 0, then dimension G minus dimension H is greatly equal to 2. So this 2 is really important for the sense normality criteria, like kind of trying to optimize these things. And okay, so we have one proof, and then John Kottner pointed out like a nice and shorter argument. The point is that dim G minus dim H, this is always even. Okay, and if it is equal, then H is equal to G, and what you have to do is to verify that this does not vanish. And you do this first for SL2, and then kind of arguments with roots and stuff. So I think these kind of arguments are new in this thing. Okay, thank you very much for.
Are there any questions for the speaker?
Yes.
So how much kind of do you understand X gen? Okay, you're understanding it a bit with this kind of argument, but in terms of like when things become reducible, or when they become semi-simple, or when they lie in Borels, or this kind of thing. You probably supposed to repeat the question.
Right. So Matt asked, do I understand anything at all about this problem? And I would say yes. And the way we study, so this is GIT quotient. So we kind of relate this to a deformation problem for Laforgue pseudo character attached to this profile. And we show that this is like universal, finite universal homomorphism to the space. Okay.
Is that R that's hidden behind there, the universal pseudo definition?
Sorry?
There's like a green R that hidden on the board.
Yeah.
You can't see, but
Well, no, this is something, well, can be defined, but it kind of comes out. So there's another thing called XPS, G, and this is universal. So this is finite universal homomorphism. So there's some kind of difference between these things, but it's only maybe up to P torsion and so on. And so we expect that this is an adequate homomorphism, just like in the theory of alpha. But we're still we're missing a little piece on a generic fiber. But well, sorry. So let me. Okay. So, but this thing you can stratify according to the levies or G levies, and the way this whole thing works. So okay. So you practice into strata, and you study the fibers of this map. So we can bound the dimension of the fibers. And so this map is very far from being flat. so dimensional fibers can jump, and this is where, I mean, this H2, yeah, so there's some defect. Okay, so, and this is where, yeah. Sorry, so if so, what we kind of know if it's like a jump in a dimensional fiber, there is a defect, then corresponding semi-simple representation has to have a small image. And there's a further very important ingredient. So in a most modern version is to Kotner, which says that Hn, the GAT to H, Gn, G is finite. So G is maybe some generalized reductive group. Components here, if I like. So this is just n tuple, and H is a reductive subgroup. So this map is finite, and you can use this to have a finiteness map between the pseudo character. And this is one input in the induction. But I'd say we'd have like quite a good I would say we'd have quite a good control of the situation. But I mean, of course, it depends what at the end of the day you want to know exactly.
Any further questions?
Can you prove that you have Durand leaves?
Yeah, so Pierre asks whether I can prove that we have Durand lifts. So not really. I mean, so there's like a version about, or this question that we're thinking about at the moment. What happens if you replace G by a parabolic subgroup? So this is, you also have like a contracting action of GM that contracts this to a levy. You also have like a similar argument. But whenever I try to make such arguments, we get very close to the arguments already in Hamilton G's paper for GLD. So it kind of turns me off immediately.
Maybe we can thank the speaker again.